In this video, we're going to be talking about energy diagrams. We're also going to be talking about enthalpy. Now, enthalpy is a concept that's closely related to energy. Recall that internal energy, denoted by the symbol capital E or sometimes capital U, is the total of all of the energies that are in a particular substance. We're talking about energies of translation, rotation, vibration. We're talking about potential energies, kinetic energies, all that good stuff. Enthalpy, which is denoted by a capital H, is defined as the sum of the internal energy and the product of pressure and volume. We don't use this equation in AP Chemistry, but it's in your textbook, which is why I'm mentioning it here. Sometimes you'll see it like this, H equals U plus PV, that's the same thing. In AP Chemistry, we don't tend to use enthalpy. What we do, however, use is change in enthalpy. And change in enthalpy is the net energy change of a process. The symbol for the change in enthalpy is delta H, but sometimes you'll see it written like this, delta H naught, and we say naught when it has a little circle that looks like a degree. This little circle indicates that a process is taking place at standard temperature and pressure. The equation for change in enthalpy is delta H equals delta E plus P delta V. Again, we won't be using this equation, but notice the P delta V term. This represents pressure volume work. So if there are pressure changes, such as those that happen when a gas expands, this is going to contribute to the enthalpy of a system. But if the pressure is constant, which it often is when we're doing chemical reactions in a test tube at atmospheric pressure, we can derive a relationship that's very, very useful. In your textbook, there is an algebraic derivation where they use this equation and delta E equals Q plus W to prove the following. At constant pressure, where no pressure volume work is being done, the heat flow for the process is equal to the change in enthalpy. In other words, delta H equals Q. And we're going to be using this relationship a lot in the next several topics. So a lot of the time we're going to be able to use delta H and Q, Q stands for heat, interchangeably. However, remember, this relationship only holds at constant pressure. If the pressure is changing, as it might with an expanding gas, then delta H does not equal Q, and we can't use this relationship. There's pressure-volume work being done, but most of the time we'll be able to estimate delta H as Q, as heat. The change in enthalpy of a system is going to be equal to the heat gained or lost by the system. You can write it in equation form like this, where delta H equals the delta H final minus the delta H initial. Change in enthalpy is what we call a state function. That means that the magnitude of delta H depends only on the initial and final state. It doesn't matter what path we took to get there. As you should remember from the last topic, we always look at enthalpy changes from the point of view of the system. If energy flows from the system to the surroundings, the process is exothermic. Delta H for the reaction is going to be less than 0 for an exothermic reaction. If energy flows from the surroundings to the system, the process is endothermic. The delta H for the reaction is going to be greater than 0. Note that the sign convention for delta H is similar to that of Q and W. Positive if the system is taking in energy, negative if the system is losing energy. Endothermic and exothermic physical and chemical processes can be described using energy diagrams. Breaking bonds or overcoming attractive forces always requires energy. Remember, it takes to break. And activation energy, which you've seen before, is the energy that's needed to break the bonds or overcome intermolecular forces. When you form bonds or as particles are drawn together by intermolecular forces, these processes usually release energy because forming bonds and attractive forces is energetically favorable. Whether a reaction is exothermic or endothermic is going to depend on the balance of energy required to break bonds or attractions and the energy required to form bonds or attractions. If the energy that's needed to break the old bonds and attractive forces is greater than the energy released when new bonds and attractions are formed, the reaction will be endothermic and delta H will be positive. We can see this in an endothermic reaction energy diagram. In this diagram, delta H is the energy change between the products and the reactants. The amount of energy needed to break the bonds and get to the transition state is greater than the energy that's released when the bonds are made. Delta H, the final minus the initial, is positive, and the reaction is endothermic. The products have a higher potential energy, which means they are less stable than the reactants. The reaction is energetically unfavorable, and energy needs to be put into the system. This energy comes from the surroundings. That's why if you happen to be in the surroundings, or if your hand's touching the beaker or flask, you'll notice that the surroundings get cold, and that's because the energy from the surroundings is going into the system. By contrast, if the energy to break the old bonds and attractive forces is less than the energy that's released when new bonds and attractive forces are formed, the reaction is exothermic and delta H will be negative. The system is losing energy. This is a reaction energy diagram for an exothermic reaction. In this diagram, delta H is the energy change between the products and the reactants, and the amount of energy needed to break the bonds and to get to a transition state is less than the energy that's released by making the bonds and attractions that are needed to form the product. And because the energy of the products is less than the energy of the reactants, delta H is going to be negative. You're taking a lower energy and subtracting a higher one. That's going to give you a negative number. So to summarize, a physical or chemical process can be described with an energy diagram that shows the endothermic or exothermic nature of that process.